Hello, everybody. Welcome, and thank you for joining us today. You are part of the 250 people worldwide who have registered to this webcast powered by Yole Développement, Benck, and System Plus Consulting. This webcast is entitled Smartphone Camera Trends. My name is Faisal Kamasi. I'm a Global Sales Support and Coordination Manager for Yole Développement. Before we start the webcast, let me give you some basic information on this online event. You have the possibility to submit questions during all the webcasts. You can use the Ask a Question window at the bottom of the screen. We will answer as many questions today as we can, and for the remaining one, we will follow up with you via email. Concerning the materials, please note that the presentations are already available and they can be downloaded from the resources section of the platform. Furthermore, you will receive tomorrow an email with the link to the recorded webcast session. So let's start the webcast. I'm pleased to welcome the three speakers of this webcast. Pierre Cambou, Principal Analyst Imaging at Yole Développement, Dr. Mikko Soderland, Semiconductor Sales Director at Benck, and Audrey Larache, Technology and Cost Analysis, MEMS and Display at System Plus Consulting. Our three speakers will share with us their knowledge and expertise. I'm pleased to welcome as our first speaker, Mr. Cambou. Pierre, the floor is yours.
Thank you, Faisal. And hello to everyone. Welcome to this market and technology brief on smartphone camera trends. I will spend 10 minutes covering the major trends for this very important device, which you have on the back and on the rear of your smartphones, and which is constructed really upon the CMOS image sensors chip, but not only chip, optics, and many other mechanical elements such as autofocus and optical image stabilization, and new to the sub components, illuminators for 3D cameras. So more precisely, this construction is usually there is a flex rigid substrate or could be ceramics with connectors. Then on top of that, image sensors. So this is typically the semiconductor device that we monitor here at Yole Développement. And on top of that, actuators, actuator drivers, which is also a semiconductor chip, metal shields, air cut filters, which is also asking for layer depositions, and we will have today a description from Benck of some of the tools that are being used for such. Actuators, lens set, again, plastic molding parts, but also using anti-reflective coatings, lens mount on top of that to finish the enclosure. So in the end, module assembly has become a huge industry, and we will see some of the trends, underlying trends. So why did it become such important industry? Initially, CMOS camera modules were invented to serve, or actually the technology itself was invented for webcams. and really it helped. It was the growth was on the back of the computing and the computers. So here in this graph, you see the volume of computers being produced every year. And actually, there is another trend, which is the digital camera trend that became the dominant way we were taking pictures by 2000. Was in the range of a few tens of millions up to 130 millions cameras by 2012. So all this got disrupted by smartphones, and really this is why the camera module industry became so huge. Is because of the numbers, of smartphones reaching 1.5 billion in 2016. Since then, we have hit the ceiling. It's going down, but cameras are still increasing. So let's go a little bit more discussing the numbers of cameras. So first, we need to look at the number of smartphones. We just mentioned that it was a ceiling around 2016. Since then, the volume has been eroding, despite all of our forecasts. We thought optimistic forecast. Now we think, for example, for 2020, even though the COVID-19 got a big hit on most of the industry, we still believe 1,250 million phones will be produced this year. Because of the recession, we think even less in the 2 next years, but then growth should resume. For cameras, this is not, we don't see any recession because the number of cameras per phone is increasing. Before I go to the, yes, so, and it is increasing primarily due to the strategy of the main players. And here we are just discussing the main players: Samsung, Huawei, Apple, Xiaomi. All those OEMs have embraced multiple camera approach, and therefore from one we've been going to dual, triple camera setups. And therefore here is the volume we get for camera modules. So the order of magnitude is 6 billion. So this is really impressive number, and the growth around 8% per year. So we still think there will be a slowing growth in the next few years, but again, this is still 8% growth, which is really nice. So this is mainly, so the orange is the mobile, and you can see in terms of volume, the rest is less than 10%. But it will increase a little bit. It will move toward 15% if we consider the revenues. So now let's look at the underlying technology trend that is powering the industry. First, a small discussion on the image sensor. So image sensor, CMOS image sensor have transitioned from front-side illuminated to backside illumination. And then more recently from stacked TSV, so through silicon vias, so to do the connection with the top and lower wafer, and then more recently hybrid stack. So you can see that what makes it very special in terms of technology is the color filter array and the micro lens array on top of the technology. So those are organic elements, and the next presenter from Benck will explain how to make deposition of, for example, anti-reflective coatings on top of those microlens. Organic microlens is a key enabler for this technology. Therefore, in terms of production, I mentioned the 6 billion camera modules. Now, in terms of kilo wafer per year, we are in 12-inch equivalent. This is we are talking in the range of 2.7 million in 2019 and reaching 3 million in 2020. The growth is 6%, so it's less than the volume of modules because there is the stacking. So I'm just talking the top part. Actually, if we think of the whole semiconductor content, it is increasing quicker than volume. I mentioned the 12-inch equivalent. Now there is a split. There is a market mix between 8-inch and 12-inch, so 300 millimeter and 200 millimeter. So right now, the CIS industry is bringing more capacity in 12-inch, most. But it is also there is an interesting market for 8-inch. And actually, in terms of just revenue and volume, it is increasing. So there is added capacity in 8-inch too. So if we look at so this market is really performance driven. We have not gone to the old days where it was really cost driven between 2000, 2005. Now we are really performance driven, and the key driver is to improve photography image quality. It is to be able to integrate the camera flawlessly into the smartphone. So the aesthetics is super important. And last, to use those cameras as a user interface, this is the 3D sensing and also the optical fingerprint under display type of cameras. So this is the last driver, very important in especially last year. So if we count the number of cameras per phone, I was mentioning initially, it's really rising sharply. So we are beyond 3 cameras per phone in average. Some phones have 4 cameras on the back and 2 to 3 cameras on the front, taking into account the optical fingerprint. So we expect this number to rise and to reach 5 by 2025. So if we have to summarize the different trends, so first talking about the past, so 10 years ago, the goal was really to improve photography and video. Then more recently, by having high quality cameras on each side and high resolution. More recently, to improve on specification and image quality and also provide this human-machine interface, then we had multiple camera trend. In the future, I think the 3D cameras will be more and more integrated, and the need for under-display camera will rise. So this is already the case for optical fingerprint. And in the future, the integration of other type of cameras, more than 3D, go beyond 3D, other type of spectrum maybe, and also the ability to use AI upscaling. So let's discuss a little bit this key trend of AI, I think, is something that will have a huge impact on the CMOS image sensor and also the cameras. Because to put computing next to the chip or next to the image pickup device is super important, and the decision will be made either to move this computing away using 5G, or to keep it close and use maybe computing within the image sensor. So this will be the big decision, and we'll see both actually. And this will transform the way the image sensor are designed and the way camera modules are made and being used. Therefore, here is my last slide. So far, camera module industry was dominated by the proliferation of cameras, especially in the number of cameras per end device. We had more of the same. Now there is a large diversity of application and technology, and Audrey will show you some of the diversity we've seen on the market, and it is providing more momentum to the camera module industry. Right now, the camera modules are very precise optoelectronic components. They contain many subcomponents, image sensor, lens, actuator, and assemblies, multiple assemblies, IR filter, VCSEL, driver ICs, Hall sensors. This is really connectors. This is making the ecosystem extremely rich. We have reached kind of a climax in terms of complexity, and I think it's going to be difficult to find the next step, and probably disruption. I mean, the industry is really ripe for disruption at this point. This is my conclusion, and Faisal, maybe we can move to the next presenter.
Yes, thank you very much, Pierre, for your presentation. Now, yes, as Pierre mentioned, let's now welcome our next speaker, Dr. Soderlund, if you please.
Thank you, Faisal, for that introduction, and good morning, evening, afternoon, everybody. Welcome to this webinar also on my behalf and also Benck's behalf. First of all, really appreciate the nice technology and market analysis shared by Pierre. Excited to see, obviously, the trend of increasing amount of cameras coming into mobile phones, even though the phone business is dropping a little bit, because that's really, and also addition of sensing onto these mobile phones, because that's really driving technology innovation. For my talk, I want you to switch your heads a little bit from the market and technology onto a wafer level. So we're going to talk about thin film coatings. And those of you in the audience who are, essentially looking at how to further enhance, improve the sensor technology and some of the optics, I think this should be attractive, especially if you're looking at improving let's say, controllability and precision of your thin film coating. So deposition as a uniquely qualified solution for those needs. I'll start with the similar explosion image as Pierre was showing from Oppo, and with a few little less details on that. But what you see here obviously is a set of optics, and at the core of it, at the heart of it, is a sensor. Today we're seeing some of that optical functions being brought onto the wafer surface, so I'll talk about that too. Generally, the interest here is further to improve, and this is kind of my challenge and opportunity slide. So is to improve the dynamic range and sensitivity of these devices, have better low light performance, increase signal to noise ratio, prolong the sensor lifetime by encapsulating it. There are more organic elements, both in the sensing as well as in optics, coming into play. Those need to be protected also. And then, yes, integration in chip scale for these applications. This is a little features and benefits slide. ALD is a gas phase process. I'm sure most of you have heard about that and know that. That's used in advanced memory and logic. Courtesy to this sequential process, it's really gentle deposition process. So you can imagine doing that also, for example, on organic layers. It produces very dense, pinhole-free coatings with extreme conformality, as well as precision. So control and precision is something that I want you to remember from this talk, if nothing else. We can do that process in a fairly wide deposition temperature range. So I put here 70 degrees C to 400. It also means that you can then essentially choose at which phase of your production flow you do that. You may do it in higher temperature in a wafer level, or at the later stage in a packaging level. It comes with the easy process control, repeatability, and we can reach significant throughputs by essentially batch processing. So not processing one wafer, but 25 wafers in what we call a mini batch. Very important for CMOS image sensor is the ability to control the materials. We have not a massive selection of materials, but a few nice oxides and nitrides, and we can pretty flexibly mix them and laminate them to produce desired and targeted properties. For example, refractive index, specific charge of the film, density and stress, and so forth. So I'll give you a few examples as we go along. Just want to click on those images to show. So these little berries on the plate that you see, these are actually kind of a few hundred nanometer sized polymer spheres, which have been coated with aluminum oxide. You can see really that the coating is conformal. Then the nanolaminates pictures hopefully comes through in a larger image. You see two oxides, high and low index, running through this nano shape very conformally around that. And the high aspect ratio essentially showing that we have the same coating thickness at the top of a trench and at the bottom of the trench. So that just gives you some indication of the, let's say, power of that technology. So where does it come to play in the backside stimulated CMOS image sensor? We go now onto the very surface of the silicon on the backside. There are three applications, three layers that I'll talk about in more detail. First one being the passivation of that sensitive surface to improve efficiency. The second point is an anti-reflective coating. Again, the silicon surface would be reflecting quite a bit of that incoming light unless you do something about that. And then as a third topic, I'm going to talk about barrier coatings. Again, these are then layers that come a little bit later. So you typically have your color filters and optics on wafer. We would be protecting that stack as well as combining it with an anti-reflective coating in one go. Going quickly to the backside passivation topic. So the passivation actually serves two functions. There's the chemical and field effect passivation. Chemical meaning that we are essentially reducing the defectivity on the surface, and you may choose a specific film based on that requirement. Field effect passivation comes into play as you deposit, for example, aluminum oxide, having a negative fixed charge, and that's going to help you drive some of these photo-generated charges into the silicon and away from the surface, away from recombination, hence improving efficiency. ALD performs well in terms of the other processes available, in terms of the efficiency, in terms of bandwidth or wavelength of operation, and best of all, it's easy to combine the passivation layer with a capping optical layer, essentially to combine passivation and an anti-reflectant function, which I'm going to talk about here. So again, these are all sitting on top of on the backside of the silicon, passivation, and on top of that, in its simplest form, it will be just a high index layer with an index in between air and silicon that will help to drive the light into the silicon. We have some nice oxides with ALD, silicon dioxide being the lowest of index, and titanium dioxide being the one with the highest index. So anything in between you can actually do by mixing these materials, either by layer or laminates. And then there may be other rationale for choosing depending on the wavelength of operation. For example, if you're looking at very much shorter wavelengths, not for cameras necessarily, but for other applications, you might be choosing hafnia over titania, which has some UV range absorption. So again, it's all about control in terms of these material properties. Also, ALD has excellent precision on the coating thickness, so you can imagine doing a 200 millimeter or 300 millimeter wafer with excellent uniformity and doing multi-layer stacks on top of them, being well controlled across that full surface area for a specific targeted anti-reflective coating performance. Then another optical application is when you would be then applying an optical element on top of your pixel. So this would be, let's say, wafer level anti-reflective coating. The image on the left-hand side from Sony is describing kind of sub-pixel architecture where they have an optical element top, essentially collecting efficiently light onto that specific pixel, and you see that really is a 3D shape. And if you wanted to apply an anti-reflective coating on that, you would be challenged with some of the existing technologies out there or other alternative technologies. Again, I'm pulling this image I showed before on this sphere. Again, aluminum oxide deposited at 80 degrees C is able to very uniformly coat a sphere all around that with nice coverage. Why is that relevant? Well, if you look at the right-hand side image about showing the reflectance, a conventional technology would be giving a right target thickness on a direction D, but then if you go 90 degrees C, 45 degrees C to A and G, well, your coating is 20% thinner, and you're not going to get the AR function you want. Whereas with ALD, that's going to be conformally coated everywhere, as demonstrated by this nice paper from Pfeiffer from Vienna. The third topic I wanted to touch upon in more detail is the encapsulation or moisture barrier. Again, there's various things on image sensors, the plastics, but also some organic sensing layers that you want to be protecting for the lifetime of the device. And really, with ALD, what we're doing is combining kind of best of both worlds. We could take an aluminum oxide, which is an excellent gas barrier, and combining that with some other oxides like zirconia, hafnia, and titania to essentially improve the chemical resistance. And we do what we call the nanolaminates here on the left-hand side image you see. And when you do that, you're essentially generating excellent moisture barrier. So we can reach down to 10 to minus 6 grams per square meter per day moisture barriers at thicknesses less than 100 nanometers. That may not say anything to you, but it's as good as glass. So it's the same as you would capping your device with glass, except for ALD, we talk about such thin layers that are not really adding to the weight or shape of the device. So that's a completely new way of essentially packaging devices. We actually started on this through OLED, and that image is showing an OLED dip on water. So I don't recommend to do that, but you could do that with an ALD layer and have it sustain lifetime performance. What I didn't mention is that this process, the encapsulation, the results here are all done at 90 degrees C. So again, this is compatible with most organic materials that you might be considering using. It also means that, again, you could be doing these coatings on the wafer level, a later stage in the module level, or even in a later phase as you package the device, because some of these materials may be sensitive to high temperature. Given some more time, I would like to dive in deeper also here, where some quick examples about designs where you're essentially looking at a higher surface area of silicon, either by generating some kind of diffractive light trapping pixels or essentially using black silicon, more a futuristic topic. You can obviously see with these structures as well as the capacity trench isolation that what you really need is a conformal coating technology to start to enhance the properties of such devices. On the same class, of course, in terms of the aspect ratio, is a true silicon via for 3D integration, where ALD is obviously being used also. Good news is that there is a tool out there that can put it all essentially together, and we're proud to present Benck Transform. That's the cluster tool, ALD cluster tool that we've introduced, specifically designed and engineered for the more than more markets. A few unique features on that tool is really the versatility in terms of combining different processes, thermal batch, together with single wafer plasma processing, and a large number of modules essentially to increase the tool capacity, the productivity. We have a little module there on the cluster tool, which is used for preheating the wafers. So we turn the ALD tool really into productive element. It's not furnace to heat up the silicon, but really to do the ALD processing as soon as the wafers are loaded in there. So that gives a massive throughput increase. It's a fully fab-ready tool, so comes with an automation, anything between 3 and 8 inch, and obviously a large share of the image sensors is today in 12 inch. We are delivering modules already, and a full solution with handling everything is coming out latter part of next year. In terms of the processes, so that's what you saw before. They are implemented on the transfer tool, the common oxides, and some of the nitrides, even for TSV applications. And generally, the tool comes with these processes with very good uniformities, less than 1%, 1 sigma, within wafer to wafer, and batch to batch. I should mention there are 2 versions of that, a light and a larger one, which essentially gives you more flexibility for a number of modules. If you're really looking at large quantity of wafers, then that's your tool to chew the transform. To give you a feel, I mean, many people associate ALD with slow and expensive, so I want to wash that out by giving you our promise in terms of throughput for a single module. The example gives for 50 nanometer aluminum oxide, which would be a decent film for passivation, encapsulation, as well as optical element. So the single module is generating 15 wafers per hour, and obviously you can add more modules to increase on that capacity. Last but not least, for those of you who are getting excited and thinking about that's a nice technology, where else are you using that? Obviously, advanced memory and logic is the core of ALD to a large part of the market. Just wanted to quickly show you that in addition to the CMOS image sensors, Benck is active in growing markets such as power devices, RF filters, RFCs, and photonics. And photonics obviously is now connecting very much with mobile phones too. And for those markets, again, we are providing thin films for high-K materials, passivation, nucleation seed, chemical barrier, and encapsulation is a very common thing across the different technologies. And with that, I would like to thank you for your attention and pass the torch to the next speaker. Thank you very much.
Thank you very much, Dr. Solander, for this very interesting presentation. It's time now for our last speaker to share her knowledge. Mrs. Larache, if you please.
Thank you. So good afternoon, everybody. I'm going to present you the last part of this webcast. So I'm Audrey Larache, and I am a display and sensor cost analyst at System Plus Consulting. And today I will present you the latest technology trends on flagship smartphones camera. So let's start. First of all, I want to present to you this little graph where we can show the number of visible camera modules we have in each smartphone since 2016 in the 3 main OEM, Apple, Huawei, and Samsung. So I select the best 1 series for each OEM, P series for Huawei, iPhone for Apple and Galaxy for Samsung. So as we can see, there is an increase of the camera numbers. To show you the last trend, I select the 3 last high-end smartphones from the 3 main OEM. So iPhone 11 Pro from Apple, Galaxy S20 Ultra from Samsung, and P40 Pro from Huawei. We don't have the iPhone 12 now because its release is scheduled this month. On this slide, there is the release date of each smartphone I have selected. We can show there are 4 visible cameras in each smartphone, 3 on the rear face and 1 on the front. On the rear face, there are 3 cameras with the same function, so 1 main camera, 1 wide-angle camera, and the last telephoto camera. We have opened each smartphone and their visible camera. These double pie charts show what we found in each camera in terms of proportions. So we have 4 cameras per smartphone. The circle in the outside is divided in 3 equal parts. And in the middle, the pie chart corresponds to the proportion of the number of CIS manufacturers we found. So Sony represents 3/4, and the last is from Samsung manufacturer. This slide shows you which manufacturer the OEM choose to integrate in his smartphone. For Apple, there is always a Sony CIS for visible cameras since many years. For Samsung, they integrate only Samsung semiconductor. They want to keep it internally, but in their last smartphone, the Galaxy S20 Ultra, the telephoto camera placed on the rear face used a Sony die. Maybe for integration reasons, I talk more about it after. For Huawei, 2 years ago, they used mainly CIS from Sony and a little from OmniVision, but now they integrate only Sony's sensors. Just as a reminder, I'm only talking about a visible camera here, not 3D camera. With this both schema, we have a big part of process used in CIS smartphone today. So Sony used since many years only copper-copper hybrid bonding. This technology has the advantage to permit to do connection directly under the pixel, and this allows to have a better ratio pixel array per die area. For the Samsung process, they must do the connection with TSV outside the pixel array. So let's go to the next slide to illustrate this point. Yes. Here we have 2 similar CMOS image sensors, but for different manufacturers. On the left, we have Sony, and on the right, this is a Samsung sensor. The 2 CIS are similar in terms of resolution, around 30 megapixels. Pixel size, in terms of pixel size, 1.4 micrometers, and technology node 2 for the logic circuit, 45 nanometers. So the TSV area, which is outside the pixel array, is circled in red color. So the TSV required more space. The die area is impacted because we see that we have about 45 square millimeters for the Samsung's die against 40 square millimeters for the Sony one. the pixel array represents 68% of the die area for the Sony against 53% for the Samsung die. There is two CMOS image sensor cross-section with the same view to show Sony process on the left and Samsung on the right. So we can see on the left the 3D stacked BSI, so backside illumination with copper-copper hybrid bonding from Sony, where the micro-LEDs of the pixel array is on the top of the copper-copper connection. And on the right, the 3D stacked BSI with TSV from Samsung, where the photo has been taken outside the pixel array. On the top of the red line, there is a pixel array circuit, and below there is a logic circuit. In the last 2 years, some OEM has begun to integrate a telephoto or periscope camera in their smartphone. We found it in Huawei and Samsung smartphone. Between both, this is the second year we found it in Huawei smartphone. Samsung has integrated it only this year. The telephoto camera is composed of lens and spacers with a CMOS image sensor like standard camera, but with a prism additional and a bigger package. This type of camera permits to have a big zoom that is not possible with standard camera because in smartphones, the integration is the first selection criterion. The camera will be thicker than the smartphone. With this solution, OEM can integrate a camera with a much larger zoom. So the particularity is that the CIS is turned at 90 degrees compared to the other CIS, and the light enters the camera by the prism. And the area of the packaging is around twice bigger. So this last slide, to recap all information we have seen. 3 big points. So the number of camera per smartphone has increased these last 5 years. Sony is the main CIS manufacturer today in the high-end smartphone for the larger OEMs. With this technology, copper-copper hybrid bonding, and the telephoto camera has appeared in some smartphones. Maybe we will find it in the next iPhone, but we must wait a little for it. Thank you.
Thank you very much, Audrey, for your presentation. We will now end up this webcast with a Q&A session. We will answer as many questions today as we can and follow up via email for the remaining one. So we received quite a lot of questions. So I've got one question for Pierre. How do you see the trend in smartphone ID regarding the camera bump on the backside? Will market still accept it in the future?
So, very nice question, very difficult question. So I mentioned in the presentation that there was, there are three drivers, but two that are connected to the question. Either will OEM prefer to boost the image quality and have a bump, so to have a bigger camera module, or do they prefer to have a flush surface and to remove the bump and prefer the aesthetics? So we have seen both approach on the market, and so far the thickness of smartphones is actually increasing. and the bump is still remaining, and therefore we can just observe that yes, it's here to stay. We also see some players trying to remove the bump. I'm thinking Xiaomi, for example, or LG. So it has no direct impact on the trend of the OEM. I think my opinion is we keep on seeing both. And as we've seen the increase in thickness, so a few years back we were decreasing and then increase again. My expectation is we could see at some point going back to slimmer smartphones, definitely. And then pressure on reducing the bump. Yeah.
Mm-hmm. Thank you, Priya, for sharing that. Thank you. One question for you, Mikko. Is it possible to do the optical multi-layer stacks in one process module, or do you need two separate modules?
Well, that's a good question. So yes, it is possible to use just a single module for doing two different materials. Obviously, we need to be matching the process temperature, but out of the list I showed for high and low index materials, we can always find a combination of high and low index material deposited in the same temperature, and hence allowing just using one module for that. So yeah, that's possible.
Okay, thank you. Let's continue with you, Mikko. One other question. What is the role and benefits of the preheating modules?
Oh, the preheater. Yeah, I went through that very quickly on the tool side. So that's essentially there to heat. I mean, we are doing a batch process to reach the rates that we talked, like 15 wafers per hour for 15 nanometer aluminum oxide. So that comes through courtesy to us heating each individual wafer before we load it into the reaction chamber. If we were to load them cold, it would take maybe 1 hour for wafers to heat up. Now, instead of that, with the preheater, we can load and heat them in 15 minutes and then do the process in a little over 45 minutes, and hence come with the throughput. So the effect of that, the importance is actually more than 50% in terms of the wafer per hour that the tool delivers. So the important module.
Okay, interesting. Thank you. Audrey, one question for you. Do dies with similar characteristics between Samsung and Sony have the same manufacturing cost?
No, they don't have the same manufacturing cost. So two points. The cost of the process hybrid bonding is cheaper than the TSV process. But for the moment, the yield may be lower. And Sony have a die smaller than Samsung with the same characteristic, with the integration of a connection directly under a pixel array. So Sony die is cheaper.
Okay. Another one for you, please, Audrey. Have you found sensors that incorporate older technology, such as the BSI standards?
Yes, we found it sometimes, but not in the high-end smartphone, and generally just in the front camera, so little resolution.
Okay, thank you. Another question for you, Pierre. Vivo X50 introduced micro gimbal stabilizer and rumor sensor shift in coming news iPhone. Is it same? And what do you see about this market trends in future?
Yeah, I think the stabilizer is part of this OIS autofocus that we've seen being introduced. There is a race there. I don't think it's going to be this time for Apple. I know they will introduce very advanced changes. I don't think it's this time. I think this time it's going to be more a fourth camera and direct time of flight. This is my expectation. Introducing more camera is extremely complex. So at the end of my talk, I was mentioning disruption. So is there a possibility that we could shrink all those cameras together and using maybe MEMS or liquid lens? I don't know. There is opportunities in this direction, and which would use a different kind of strategy than the Oppo. But yes, the trend is actually very vivid, and I think we will see a lot of innovation in this direction.
Thank you, Pierre. We still have a question, but the webcast is now over, so we will answer the remaining question by email. And we'll do our best to do it as soon as possible. You will soon receive an email with the link to the recorded session. Also, please feel free to share the presentation with colleagues. Finally, please let me remind you that you can find all our reports on our website, www.i-micronews.com. Do not hesitate to contact us if you have additional questions. You can find our contact details on the last slides of the presentation. Thank you all for joining us. Have a good day. Bye-bye.